Hi everybody, this is Miss List and I am here with Unit 4 in AP Chemistry, which is all about chemical reactions. So of course it makes sense that in 4.1 we are introducing chemical reactions. Whenever I introduce chemical reactions, I think a good place to start is a breakdown of matter. And this is something that gets discussed at many levels. It gets discussed if you've taken a physical science class. It gets discussed in like a on-level chemistry. And here we have it again in AP chemistry. It never hurts to review it. If you've already seen this, that's great. But if not, here you go. Chemistry is defined as the study of matter. And so matter is anything that has mass and volume. And we like to categorize matter into solid, liquid, gas, and plasma. Anything that is not one of those things is energy. And we like to classify matter into two subcategories, mixtures and pure substances. The thing about mixtures is that they can be easily separated compared to pure substances, which need chemical reactions to separate or rearrange them. And that's the main theme here, is that we are dealing with chemical reactions. Now, a physical change is where a physical property of a substance changes without changing the chemical composition. There are several types of physical reactions that can take place. Keep in mind that the key feature of a physical change is that the atoms are not rearranged. So properties like shape, color, texture, flexibility, density, and mass are changed, and physical changes are usually reversible. So an example of showing a physical change in a chemical reaction would be something like showing water, which we know is H2O, and we might show it go from a solid phase, which would be ice, and we can show that as a chemical reaction kind of with our yields arrow here, or becomes, and then we can show it changing from a solid to a liquid. This would be a representation of a physical change because nothing changed. It's still H2O on each side. There's not any new substance that's created. If we compare that to a chemical change though, the composition of the substance changes, which means new bonds, old bonds are broken, new bonds are formed. And the key feature is that atoms do rearrange. So for example, if I had hydrogen gas plus oxygen gas forming water, this would be an example of something chemical, because notice that the left and the right, we have different atoms and we have different substances. On the water, or on the right hand side, we created water, but on the left hand side, we have just hydrogen and oxygen. So there are signs that chemical reactions have taken place, and some of them are listed here on this list. Formation of a precipitate is when we put two solutions together and it gets cloudiness in it. You've probably seen that happen in a lab. Color change, if there is light that's given off. Temperature change, either getting it hot or cold. And the emission of a gas. This is not to be confused with bubbling. That's due to boiling. Emission of a gas would be if I mix two things together and it started to bubble. The main takeaway is that chemical changes are often difficult to reverse. There are 5 types of chemical reactions that we like to try and categorize in chemistry, and their names are over here on the left. The first type is called a synthesis reaction. This is when two elements combine to form a compound. When I do this with my students, when I teach it to them, I call this the marriage reaction. I think relationships is a nice way to talk about what's happening here. We've got two single things coming together to form one couple, if you will. The decomposition is kind of the opposite of that. We've got AB on the left, and it is breaking apart into A and B. So I call this the divorce. Single replacement, I call homewrecker. And the reason I call it homewrecker is because A and B are together as a couple, and C comes in and hooks up with A, says I'm taking A, and on the right hand side they're together, and B gets left out in the cold. So that's why I call that a single replacement, a homewrecker. A double replacement is called, I call that wife swap. That's because both partners are switching, so A and D end up together and C and B end up together. And then finally, our last common type of reaction is called a combustion reaction. I don't have a fun story for this one to help us remember it, but it's the most specific of the types of reaction because it has to be a hydrocarbon. And a hydrocarbon is exactly what it sounds like. It's some compound that contains carbon and hydrogen, and it has to be reacting with oxygen. The products will always, always, always be carbon dioxide and water. That's why it's the most specific of the types of reactions. Now, later, we're going to be talking about another type of reaction called a redox. And redox reactions can be any of these types except for double replacement. Double replacement will not be redox, but any of the rest of these could possibly be an oxidation reduction reaction, which we call redox. We'll be following that up in a later section though. So here we have just some practice on chemical changes versus physical changes. And then we've got some practice on writing and balancing chemical reactions. So in letter A, they give us the term melting, and that would be a solid going to a liquid. And in the right-hand side, they're asking us, are the IMFs weakening, breaking, or forming? And when a solid goes into the liquid form, I would definitely say that's a weakening of the IMFs. They're not completely breaking because there's not a separation of particles, but they are not being locked in place. Boiling is going to be a liquid to a gas. This is going to be completely breaking the IMFs. When you go into the gas phase, the particles are free to move about, which means that those IMFs that we talked about last unit are not interacting with each other hardly at all. A gas to a liquid is called condensing. So this would be the reformation of those IMFs when a gas is condensing to a liquid. The particles are slowing down, they're getting closer together, which allows those IMFs to form between the particles. If I go from a solid directly to a gas, this has a special name called sublimation. And this, most people know the example of a solid directly to a gas is dry ice, which is actually a misnomer because dry ice is solid going to carbon dioxide gas. So that S looks a little bad. There we go. If I'm going from a solid directly to a gas, then that would be the overcoming of IMFs. They're completely separating the particles from each other. A gas going to a solid also has a special name, and that's called a deposition. And this would be a forming of the IMFs. In our last example, we have freezing. So that is going to be a liquid going to a solid, and this is going to be forming again. Those IMFs are going to be reforming, getting stronger. That would actually be a better description. I don't have it on here, but it'd actually be better because liquids do have IMFs. They're actually just going to get stronger when we have a solid phase. All right, so for number 2, we have some predicting the products and balancing of the following reactions. So this is going to be tied to those types of reactions that we talked about. Letter A is going to be a single replacement. So this is my home wrecker. Now, that means that magnesium and chlorine are breaking up. And who is going to hook up with sodium? And it's either going to be magnesium and sodium together on the right-hand side, or it's going to be sodium with chlorine. The way we determine that is by charge. So magnesium and sodium are both positive charges. They're not going to be together in an ionic compound. So that means that sodium is going to hook up with chlorine. When I recombine them on the right-hand side, we must rebalance the charges first. So +1 and -1 cancel, so I don't need any subscripts. And I'm going to show magnesium ending up by itself. Now, I do need to balance this by adding coefficients because one of the things about chemical reactions is that we have to have the same number of atoms on each side. So sodium There's only one of those on the left, one sodium on the right. That's fine. Magnesium on the left and magnesium on the right, I have 1 and 1, but it's this chlorine. I have 2 chlorines on the left-hand side of the arrow, which means I need to have 2 on the right. The only thing I can do is add a coefficient. I cannot add a subscript. The subscript comes from your charge balancing. Now, when I add the number in front, it's very similar to math class when you have a number in front of a parentheses that counts for everything inside. So this now also counts for sodium. It fixes chlorine. I now have 2 chlorines, but I also now have 2 sodiums. So I need to put a 2 there. And that is a correctly written and balanced equation for that reaction. Our next one is going to be our synthesis reaction. And the reason I know it's synthesis is because I have K and Cl, so just one element each, and they're going to get married. They're going to combine together. Remember, when we come over to the right-hand side and we're forming new substances, we always check our charges first. +1 for potassium, -1 for chlorine. And then very similar to what I did last time, I also will need to balance because on the left I've got 2 chlorines. I need 2 chlorines on the right-hand side of the arrow. And again, putting that 2 in front now makes K 2 as well. Our next one is called a combustion reaction. And remember, it's the most specific. So I have carbon and hydrogen. That's my hydrocarbon reacting with oxygen. When I identify a combustion reaction, I don't need to think about it at all. The products are always going to be CO2 and water. A lot of students get this one confused with a single replacement, and I get it because it looks like initially you have a compound here with a single. And so you might be thinking, this is my homewrecker. However, we just have to be super aware that when we see carbon and hydrogen reacting with oxygen, that is not our homewrecker reaction. That is, in fact, a combustion reaction. For combustion reactions, they're a little tricky to balance. If I like to work left to right, when I balance combustion reactions, I notice I have 2 carbons on the left. So I'm going to start out by putting a 2 here. I'm going to do hydrogen next. I have 6 hydrogens, so I put a 3 here, and that gives me my 6 hydrogens. I save oxygen to the end because there's oxygen in 2 places on the right-hand side of the arrow. There is 2 times 2, which actually is 4 oxygens here on the carbon dioxide, and then each of the waters is going to have an oxygen. So that is 4 oxygens on the CO2 and 3 oxygens on the water, which actually gives me a total of 7. This is a problem because I can only balance with whole numbers. I can't put a 3.5 in front of oxygen. So when this happens, I tell my students to go back and put a 2 in front of my hydrocarbon. So I'm going to double everything. So now I have 4 carbons. I now have 2 times 6, which is 12, which would give me 6 times 2 on the water, 6 times 2 on hydrogen. And then my oxygens ended up working out because I have 8 on the carbon dioxide and 6 over here on water. 8 and 6 is 14. And now I can put a whole number there in front of the oxygen. So the combustion are easy to identify. They can be a bit of a pain when you try to balance them. Our next one is going to be our double replacement reactions. I know it's double replacement because I have Li and Cl, that's a couple, and I have silver with nitrate, that's also a couple. When we have double replacement, it usually goes out with insides, and that's because of the charge. Lithium's +1, nitrate's -1, so they're going to hook up. And silver is going to go with chlorine. Silver is +1 and chlorine is -1. Again, we're always checking our charges when we recombine things. We're going to deep dive double replacements in the next section when we talk about net ionic equations. There is a little bit more that we usually do with double replacement, but we're going to save that for 4.2. Finally, our last type of reaction is a decomposition, and this is where it's going to break apart. So aluminum is not diatomic, but oxygen is diatomic. So a quick note on our diatomic elements. Those are ones that di prefix atoms, they always appear as 2, but this is when they are riding solo. So we would never put oxygen just like that, because in every science textbook, oxygen is written as O2. That's because oxygen is diatomic. Nitrogen is the same way. And there's some other friends that do this. When I teach this to my students, I call them the 7 up, because they make a 7 on the periodic table. It is nitrogen, oxygen, fluorine, chlorine, bromine, iodine. That's the 7. And then up is hydrogen, because hydrogen is over here on the left-hand side. So any of these, and this is only when it's by itself, is going to be one of our diatomic elements. It's not when it's combined. Notice chlorine, when we were using chlorine over here, we didn't automatically put a 2 down at the bottom because it's not by itself, it's with potassium. So this is only when they're by themselves, which is what happens down here in our decomposition reaction. We have aluminum, which is not diatomic, breaking up with oxygen. Oxygen is diatomic. So a common mistake is students want to bring our subscripts with us over to the right-hand side. Again, we can't do that. What we can do is fix it with balancing. I notice I have 3 oxygens on the left and 2 on the right. So when you have a 2 versus 3, it's easiest to get them to balance at 6. That's the least common multiple between them. So if I put a 2 here, that's going to be 2 times 3, which gives me 6 oxygens, which means I need a 3 here. 3 times 2 is 6 oxygens. And then finally, 2 times 2 would give me 4 aluminums. All right, so that was an introduction to chemical reactions. In our next section, we're going to deep dive double replacements and look at them in more detail with what we call a net ionic equation. Hopefully this was a good refresher for you, and I will see you next time.